Good morning, everyone, and good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation series, and this time the nice topic is electrical power generation utilizing nuclear energy. Remember, I've made about 3 video presentation, YouTube presentations on different forms of electrical power generation utilizing different energy sources, and one of them is geothermal energy, and the other one is pump storage energy, and the other one is coal energy. And this time we're talking about nuclear energy. And my good name is John Kweku Amohotu, and I've been a professional electrical engineer for the past 31 years. I'm based in the United States of America and practicing as a professional electrical engineer for the past 31 years. Now let's talk about some logistics here. If you like my presentation, don't forget to select the like button, and don't forget to share this YouTube video that you are watching, and any other YouTube video sessions that I have. Also, you can subscribe to my channel, but before you can subscribe to my channel, you need a Google account, Google email, and that is Gmail. Okay, so if you don't have one, go ahead and create one, and that will allow you to subscribe to my YouTube channel that has many presentation materials that is very good for you as a development engineer, and as a mid-career engineer, as an experienced engineer, as a consulting engineer. And with that, we'll go on to the next slide. Okay, so now, I will re-emphasize and basically what I made mention in the previous slide with regards to this YouTube channel. Very, very important, So, this is my YouTube channel, Work and Happiness, Talking to the Engineer. This YouTube channel has a lot of presentation material, technical presentation material, basic knowledge, presentations that are very good for engineers that are learning the basics. For the beginning career engineer, for the mid-term engineer, mid-career engineer, and for the experienced engineer, for the consulting engineer. But what you have to do is you have to subscribe to the channel. But before you can subscribe to the channel, you need a Gmail account from Google. Okay, so if you like my presentation, right, you can select the like button and share this knowledge. Okay, so this is just a scheme of how nuclear energy is produced, right? Okay, so this one is called a cooling tower. Okay. This one acts like a heat exchanger, right? Okay, so that allows basically the wasted coolant of water that comes out of the condenser basically to be cooled utilizing river source water, and basically it returns back into the loop as a closed cycle loop. So this one is more of a heat exchanger. Over here is the reactor containment. Right? This is made of thick cement, very reinforced concrete, right, that has the nuclear energy material that is going to be used for the nuclear fission action. So basically this one contains the uranium 235 and 238 material, right? And basically this has been formed in full assembly and tied together and in a container, and basically it is immersed in water. Basically that creates once it is immersed in water, it creates the nuclear fission reaction, right? Okay, so you have uranium 235, right? Basically in the presence of water, basically it reacts and basically releases another uranium plus neutron. And that neutron basically reacts with another uranium fuel. And now basically the reaction forms, basically becomes a chain reaction. And anytime that the neutron is released, it releases heat. So think about it, millions of neutrons that are being, and basically a neutron reacting with another uranium, basically all that chain reaction releases heat. And that's how steam is formed from nuclear generation. Okay, so this is basically the nuclear power plant. So this one houses the steam turbine and the generator. Right? As you know, the steam turbine is coupled to the generator, through a horizontal shaft. Right? The steam turbine itself has a shaft that has basically turbine blades. Right? So those turbine blades has been basically, sectioned into high pressure section, intermediate pressure section, and low pressure section, right? Okay, so, and there's a coupling here, and this is the generator shaft, right? So the generator is here, and the steam turbine is here, right? Okay, so you have the steam that basically flows from the steam generator, and like I told you that this steam is very dry, about 98% dry and 2% saturation of water, and flowing in very huge piping. Think about it, the piping is very huge, and the mass flow rate is very high. So once it impinges on the turbine, it basically rotates the turbine blades, and once the turbine shaft is coupled to the generator rotor, which is also another shaft, right? Once the turbine starts turning, the generator rotor also starts turning. And basically you have your extension system that provides DC voltage and DC current to the winding of the generator. And basically this creates a revolving magnetic field. Right? Okay. So the generator has a stator and the rotor, right? The stator has windings in, and the rotor also has one. Right? Okay. So once it creates that revolving magnetic field, right? Basically, the generator starts picking up speed, and it starts building that voltage, right? So until it reaches the threshold, nominal speed of, let's say, 1800 RPM or 3600 RPM, depending on the number of poles. This is for cylindrical rotors of the steam turbines. Those are mainly about 2-pole or 4-pole. Yeah, so that's why they have a high speed, right? Compared to cylinder pole for hydros that are much slower, that have a slower speed, because the cylinder poles for the hydros have many poles, about 100 poles. Right? So based on the formula, right, that is speed is equal to 120 F over the number of poles, right? Okay, so 120 times the frequency over the number of pole pairs, right? Okay, so if you have a smaller pole pairs, right, like a cylindrical rotor, which has 2, right? Okay, so 120 times 60 over 2, that is about 1800 RPM, right? Okay. So on the other hand, if you have about 100, right, pole pairs, that translates to only 18 RPM. So that is why the generators that are basically utilized for the hydros have a slower speed. Okay. So as the rotor starts building up, rotating, it builds up the magnetic field, right? So the rotor has a speed, right? And the stator also has a basically the magnetic field is induced into the stator coil to also form another magnetic field. So you have 2 magnetic fields in place, right? You have the stator magnetic field and you have the rotor magnetic field, right? So the rotor magnetic field will rotate until it achieves synchronous rotation. Then the stellar magnetic field will also rotate until it achieves a synchronous rotation. At the time that both magnetic fields achieve the same synchronous rotation, the same revolutions per minute, that is when they lock in place, right? So that is what they call synchronous speed. So at that time, basically, then let's say about 80% of the voltage has been built up, right? Then the remaining 20%, it continues rotating at that synchronous speed until the rated terminal voltage is achieved. Okay, so now this is the reactor containment, right? Okay, so like I told you that this is a nuclear energy, right? And that is uranium 235 to 38, right? And basically, health-wise, it has to be contained because of because it can be very damaging to our health. So because of that, you have a reactor containment that is basically built with extensive concrete, right? Reinforced several times, and basically this is what contains the fuel assembly, right? You have a horizontal mount fuel assembly, then you have a vertical mount fuel assembly. So you see the fuel bundles are immersed in water, right? That water is heavy water that has a high content of deterrent, right? And basically, the reaction with the fuel assembly, the uranium fuel assembly with the water is what creates the nuclear fission reaction, right? And anytime it creates a nuclear fission reaction, it releases a neutron, right? And that neutron reacts with another uranium, right? And it creates a chain. And, when it releases the neutron, it's basically, releases heat. And when that neutron reacts with another uranium, it releases heat, right? To release another neutron. So it basically forms a chain reaction. So that heat basically is the one that heats the water. So there's a closed cycle water, right? That basically the heat from this chain reaction is what heats that closed cycle water, right? To create steam. And that steam flows to a steam generator, right? To create the required quantity of steam that is needed for the steam turbine. So remember, the previous slide, I showed you that this is a reactor containment building, and the goal of that reactor containment building is to contain the fuel assembly and contain all the fuel reaction, the nuclear fission reaction that takes place, and that releases the heat energy or the thermal energy that is required to generate steam to be used for the steam turbine to generate the required energy, right? Okay, so this is basically a picture of how a horizontal type of fuel assembly looks like and containment looks like. We also have vertical mounted fuel assemblies, right? Okay, so as you can see over here, this is the containment wall of the reactor, and like I told you, this is made of heavy concrete, reinforced, right? And basically, barriers are created inside. We have the primary containment, we have the secondary containment, and we have the tertiary containment, right? Okay, so as you can see over here, you have the primary containment, you have the secondary containment, and you have the tertiary containment. And the fuel assembly is after tertiary, right? So all these barriers are put in place to make sure that if there should be any fuel leak or whatever, it doesn't, come outside. Because when you have a nuclear chain disaster, basically, it's not good for the health of the inhabitants that are living close in proximity to the nuclear power plant. As such, all these barriers are put into place, right? The primary, the secondary, and the tertiary. are all put into place to make sure that the fuel and the nuclear fission and the chain reaction is all contained and it doesn't leak to the outside. Well, so this is an example of how a vertical mounted fuel assembly looks like. Like I told you, I showed you in the previous one. I showed you pictures of how the horizontal mounted fuel assembly looks like, but this one is a vertical mounted fuel assembly. Okay, so this is how this slide basically tells us about the nuclear fission reaction, right? Okay, so you have uranium fuel, right, that reacts with water and it creates a neutron, right? And it releases thermal energy, right? And this neutron will react with the next uranium 235 or 238, right? To basically achieve a chain reaction, and they are fast. I mean, these reactions are very fast. And basically, you see that millions of reactions are taking place, and that's hundreds of millions. And basically, it basically releases the required thermal energy that will basically create steam or a closed loop water that is flowing in the reactor fuel assembly, right? And goes to a steam generator building. Okay, so this is also another picture of how the uranium fuel assembly looks like. Okay, this is the uranium atom 235 or uranium 238. This is how it looks like. So this is a picture of a nuclear fission, right? This uranium atoms 235, uranium 238 in the presence of water, right? Remember the fuel bundle assembly, it's all immersed in water, right? And once it is immersed in water, it basically, creates a nuclear fission reaction and releases neutron, right? And neutron reacts with the next uranium atom and basically creates that chain reaction. Next is a picture of this uranium fuel, right? Right, and many of these, right, thousands of these put together in a horizontal rod. Okay, so this is how the uranium fuel looks like, and basically you have 1, 2, 3, 4, 5, 6, 7, right, and you can have about 500 to 1,000 of these all connected together, and basically it is embedded inside this sleeve that is there to contain and to form an assembly. So this is what they call the fuel assembly, right? Okay, so the picture I showed you in the previous slide, right? It's just a symbol of that, right? But you can have let's say thousands of it in just one fuel assembly, right? And you can have hundreds of fuel assembly inside the containment, right, to create the required energy that is needed. Okay, so this is how, for a horizontal mount, this is how the fuel assembly looks. So yeah, basically embedded inside, right? Okay, so 1, 2, 3, 4, 5, 6, 7, many. Like I told you, you can have hundreds, close to about 500 of them all in. So this is one fuel assembly. Second fuel assembly, third, all the way, I think we have about 500 to 1,000, depending on how big, how like the size the nuclear power plant is. Okay, so this is basically the closed loop piping that comes through this reactor fission containment, basically the heat energy or the thermal energy that is generated from the nuclear fission process is transferred through conduction onto the coolant that is in this piping, and basically it is transferred to a steam generator building. So this is another picture of a fuel assembly, and you can have about 500 to thousands of them, and tens of thousands of them, depending on how large the nuclear power plant is. Now let's talk about control roles, right? Okay, so you have a nuclear fission, right, reaction, right? Okay, so uranium atom, right, 235 238, right? That reacts with water to release a neutron. That neutron basically is going to bombard another uranium atom to create a chain reaction, right? Okay, so the reaction can be so fast that the reaction has to be controlled, right? Okay, so you have a control rods that are inserted inside, basically, based on the depth of insertion, right, to control the reaction, right? Okay, so these rods come in and out, right? Okay, it comes in and out to control the rate of nuclear fission reaction and control the rate of thermal energy that is being created. And because of nuclear energy, there has to be a way of controlling that reaction so that basically you don't have so much explosion inside the containment building. Okay, so this is the steam part, right? Okay, so you have a fuel assembly, right? And that is shown over here, right? And like I told you that it has a closed loop water system that flows through inside the fuel assembly whilst the nuclear fission reaction is taking place, right? Okay, so you have water that is flowing through that basically takes the energy through conduction, the thermal energy from the nuclear fission reaction, and basically creates a steam path that flows to a steam generator, right? To basically create more steam and get a drier steam before it is transferred to the steam turbine. Next is the steam generator. Okay, so the steam generator itself is another containment, right? Okay, so like I said, all these transfers, takes place utilizing, various pump motors, right? Okay, so we have different, reactor, circulating pump motor, different types of motors that helps to transfer these fluids to the next place that is supposed to. Okay, so you have the steam, right? That is generated from the reactor containment, right? And that flows over here, right? So you have another water that is in the steam generator, right? So this heat that is embedded, or the thermal energy that is embedded in this water that is being transferred from the reactor containment building, basically this water that is in the steam generator takes the thermal energy from it, and from there basically creates basically a dry steam, and that steam is the one that is basically piped to the steam turbine. Okay, so this is a nice picture of how the steam turbine looks like. Remember, I made mention that the steam turbine has blades, right? Okay, so this is the shaft of the steam turbine, right? And it's very horizontal, right? Okay, so, and these are the blades, right? And you have steam coming in to impinge upon these blades, right? So, as you can see over here, the bigger sizes of blades are the low pressure section, right? And the smaller size are high pressure section and intermediate pressure section, right? Okay, so the steam comes here. This will be part of the high pressure section, right? So you have some turbine blades, right? It comes here and it hinges upon it, then it starts rotating. Right? And this shaft is coupled to the shaft of the generator, and it starts generating electricity. Okay, so this is another schematic, right? Okay, remember, I told you that, this is the reactor containment building, right? And now you have fuel assemblies that are immersed in water that creates a chain reaction that generates thermal energy, and that thermal energy is the one that basically heats a closed loop water, and that closed loop water, creates steam. So that steam flows in this part, right, through this coils that is in the closed loop part, and this steam generator also has water in it, right? Okay, so that thermal energy is transferred to this water to create steam, and the drier steam basically moves up and basically into this piping and comes into the turbine and rotates the turbine, and from there it rotates the generator. So as you can see over here, this is the piping coming from the steam turbine generator, right? Then you have the steam hitting the turbine blades, right, to rotate it, right? So the turbine blades are rotating, right? Then this is the generator, right? So once the shaft of the generator and the turbine are all joined together, once the steam turbine is rotating, the rotor of the generator also rotates to generate the required electricity, which will be sent to the outside world. This is basically the transmission end, right? The step up, right? Okay, so at the terminal of the generator, right, you have a 13.8 kV. The generator, right, 21 kV, right? Okay, so it has to go through a step up transformer because you're going to transmit this voltage over long distance, hundreds to thousands of kilometers, right, or miles, right? Okay, so it has to be stepped up to a higher voltage so that to minimize the transmission losses, right? Okay, so this one can be stepped up to 115 kV, 230 kV, 345 kV, 500 kV, 765 kV. Okay, so once that high side voltage is achieved, it is integrated to the transmission network. So this is how electricity is transmitted to the outside world. So from here, then basically it's on this conductor for hundreds of miles and thousands of miles, tens of thousands of miles, which basically for those thousands of miles definitely goes through repeated substations, basically to put in the required equipment in terms of reactors and capacitor banks, to be able to sustain the voltages so that the receiving end voltage is don't deviate compared to the sending end voltage. Well, that comes to the end of my presentation, and basically you have basically listening to electrical power generation utilizing nuclear energy, and I can indicate it. I have 3 other videos that shows electrical power generation utilizing other forms of energy. That is pump storage, right, and geothermal energy, and also energy from fossil, right. So this is my YouTube channel, and this is Working Happiness. Has a lot of presentation materials and learning materials on it. You as a young engineer starting your career, and even in college, and as a mid-career engineer, as an experienced engineer, as a consultant engineer. Okay, so if you like my presentation, don't forget to select the like button and share. And also, you can subscribe to my YouTube channel. For you to be able to subscribe to this YouTube channel, you need a Gmail account from Google. So go to Google and create a Gmail email, then you should be able to subscribe to this YouTube channel and any other YouTube channel that you want. Well, that comes to the end of my presentation. Thank you so much for your listening ears. Then again, my good name is John Kweku Amotu. I am a professional electrical engineer for the past 31 years and practicing as an electrical engineer for the past 31 years in the United States of America. With that, I say thank you.